Let us start KiboCUBE Academy Lecture 27, Introduction to Small Satellite Constellation. I am Ryu Funase of the University of Tokyo, and I will be giving this lecture. Let me briefly introduce myself. When I was a graduate student at the University of Tokyo, I was involved in the development of Psi-4, the first CubeSat in the world, and Psi-5, the second CubeSat in our laboratory. Later, at JAXA, I was involved in solar system exploration missions such as Icarus, a demonstration mission of a solar sail in deep space. After that, I have been leading deep space exploration missions such as PROCIUM, the world's first microsatellite deep space mission, and Eclipse, a 6U CubeSat that was launched on NASA's SLS Artemis 1 mission. As a professor at the University of Tokyo and JAXA, I have been working on new space development with small satellites, especially in the field of deep space exploration. My area of expertise is spacecraft system design and navigation guidance and control of spacecraft. The structure of this lecture is as follows. First, as an introduction, the recent evolution of small satellites will be explained. Then I will explain what a constellation is, which is the topic of this lecture, and what role small satellites play in its realization. In Chapter 2, I will explain the purposes for which constellations can be used. I will introduce some of the types of missions in which constellations are used, provide some examples of early constellations, and then present some representative examples of constellations that have been built or are being built today. As a theory behind these examples, Chapter 3 covers orbit dynamics and orbit control, which are key to the design and utilization of constellations. Chapter 4 provides an overview of the various challenges in realizing small satellite constellations. The challenges include not only technical issues, but also regulatory issues. Chapter 5 introduces the future direction of small satellite constellations. In addition to the possibility of realizing more advanced constellations, this chapter also discusses formation flights, which are missions using multiple spacecraft as well as constellations, and the possibility of constellations beyond Earth orbit. In the last chapter, Chapter 6, I would like to summarize the contents of this lecture. So now I will start with Chapter 1, Introduction. In this chapter, I will explain the recent development of small satellites, then define a constellation, which is the topic of this lecture, and explain how small satellites can play a role in realizing the constellation. Over the past 20 years or so, we have seen a growing trend toward the launch of small satellites weighing less than several hundred kilograms, rather than the conventional satellites weighing more than 1 ton. There are various categories of small satellite weights. Satellites weighing several hundred kilograms are called small satellites in the narrow sense of the term. Microsatellites are weighing from 10 to 100 kilograms, and even smaller satellites are called nanosatellites or picosatellites. This chart shows the number of satellites weighing 50 kilograms or less launched each year, which has been increasing rapidly since the late 2010s and is expected to continue to do so in the future. This rapid growth in the use of small satellites has been driven by a rapid increase in the capabilities of small satellites. When the world's first 1U CubeSat was launched in 2003, the capabilities of such a tiny satellite were extremely limited. But since then, with the advancement of ground-based electronics technology, the miniaturization and improvement of the performance of small satellite equipment has progressed, and small satellites are now able to perform sufficiently practical missions. As a result of these developments, more and more small satellites are being launched and utilized. The theme of this lecture is about constellations using such small satellites. Before explaining about small satellite constellations, I would like to explain what a constellation is. Most people probably imagine that a constellation consists of many satellites orbiting around the Earth, as shown in the right figure. Although it is not clear from this figure, a constellation is not just a large number of satellites, but there are some more essential elements to a constellation. The IAU, International Astronomical Union website, has the following description. Over the past decades, considerable effort has gone into designing, building, and deploying satellites for many important purposes. Recently, networks known as satellite constellations have been deployed. Constellation deployments are being planned in ever greater numbers in mainly low Earth orbits for a variety of reasons, including providing communication services to underserved or remote areas. A satellite constellation is a number of similar satellites of a similar type and function, designed to be in similar complementary orbits for a shared purpose under shared control. In other words, a constellation is not just composed of many satellites, but a group of satellites with a common function and style, with a certain common purpose, and the orbits in which they are placed are similar and complementary. Therefore, when considering the deployment of the same type of satellites into similar orbits, the utilization of small satellites is key to the realization of the constellation in terms of development cost, development time, and launch costs. One of the objectives of a constellation is to achieve global coverage. In this sense, geostationary satellites achieve the same objective. Satellites placed in orbit at an altitude of about 36,000 kilometers can provide constant monitoring and achieve high temporal resolution, but not high spatial resolution. In contrast, a constellation in low Earth orbit can achieve high spatial resolution due to its low altitude, but the time resolution with a single satellite is extremely low, so many satellites must be deployed to visit the same point one after another to achieve high temporal resolution. Although the number of satellites increases to achieve high temporal resolution or spatial coverage, the cost of developing and launching many satellites can be kept within a realistic range because high performance in terms of spatial resolution can be achieved even with small satellites. This system consists of a large number of satellites, which makes it robust against satellite failures and highly compatible with the style of small satellites, in which satellites are repeatedly launched and improved based on experience. It also has the advantage of being able to be gradually replaced for maintenance and performance improvement. In this way, the use of small satellites is the key to building a satellite constellation, and many of today's constellations are composed of small satellites. In Chapter 2, I will explain the objectives for which small satellite constellations are used. After introducing some of the types of missions in which constellations are used and presenting some early examples of constellations, I would like to present some typical cases of constellations that have been built or are being built in the present day. As explained in the previous chapter, satellite constellations have the major advantage of global coverage by multiple satellites and frequent visit to the same locations. The most obvious application of such a constellation is for navigation, as in the case of GPS, where a receiver on the ground can calculate its position by receiving radio signals from multiple GPS satellites. There are also satellite constellations for communication between users on the ground through space, and Earth observation constellations for frequent observation of the whole Earth. Recently, satellite constellations for IoT, Internet of Things, are also being planned to connect all kinds of objects on the ground to the Internet. In this way, constellations have the advantage of covering a wide area of the Earth by placing many satellites in low Earth orbit and reducing signal delay between users in satellite communications. Various applications have been developed by taking advantage of these features. The concept of constellation is said to have originated with the US Navy's Transit System, or NavSat, which began operation in 1964. It is a constellation of navigation satellites arranged in 5 polar orbit planes, each with an altitude of 1,100 kilometers and a period of 106 minutes. In this system, the ground terminal can basically see only one satellite at a time, and the user can only determine its own position in 2 dimensions. In other words, the system had weakness such as being unsuitable for determining the 3-dimensional position of aircraft and other objects. As a way to overcome this weakness, a new navigation system has been developed that can also determine the position of such high-speed moving objects. This is GPS, Global Positioning System. The GPS, Global Positioning System, Constellation, is designed to have a minimum of 4 satellites visible at any time, and can determine the 3-dimensional position and time of a user at a low altitude than the GPS satellites. The orbit of the satellite is MEO, medium Earth orbit, with an altitude of about 20,000 kilometers and an inclination of 55 degrees, and is designed to cover the entire mid-latitude region except for the polar regions in the southern and northern hemispheres. The orbital period is approximately 12 hours, and each satellite passes over the same location twice a day. There are 6 orbital planes, each with an ascending node on the equatorial plane spaced at 60 degrees. At least 4 satellites are placed in each orbital plane, making a total of 24 satellites in the base configuration. Since its full-scale operation in the 1980s, GPS has undergone a series of upgrades and is still in operation. Although initially limited to military use, it was later opened to the public. In the early history of satellite constellations, Iridium, a constellation for communications, is another notable example. The Iridium system was designed to meet the growing need for global communications coverage, including communications needs in areas with insufficient terrestrial communications infrastructure. The satellite orbit is a polar orbit with an altitude of 780 kilometers and an inclination of 86.4 degrees. 11 satellites in each of 6 orbital planes is the base configuration, which enables seamless coverage. Later, the company was reorganized and the Iridium satellite system was reopened and is still in operation. From here, I'd like to introduce some representative examples of small satellite constellations in the present day. Compared to the early stages of satellite constellations, satellites are now smaller, less expensive, and easier to launch, so more and more small satellite constellations are being built in various application areas. One of the most successful small satellite constellations is Starlink by SpaceX. Starlink is a constellation for communications with an estimated 7,000 satellites in low Earth orbit as of January 2025, covering the entire area of the Earth. The orbits are divided into several groups with different altitudes and inclination angles. The satellites have been continuously upgraded. The initial versions of the satellites weighed about 300 kilograms, but they have become larger and larger as more advanced functions have been implemented. One of these features is inter-satellite optical communications. In addition to increasing the number of satellites to improve coverage, the ability to relay communications at high speed is being expanded through high-speed optical communications between satellites. In addition, the use of highly efficient Hall thrusters has made it possible to maintain orbit and avoid collisions with debris. Direct communications with cellular phones on the ground is also being implemented. Starlink consists of a large number of satellites, so it is important to launch them efficiently. As shown in the right figure, each satellite has a flat structure, and by stacking them vertically, the volume of space inside the rocket fairing can be fully utilized to achieve efficient launch costs. Next to communication applications, another typical constellation application is GNSS, Global Navigation Satellite System. At the beginning of this chapter, I introduced GPS, Global Positioning System, which has been constructed since the early days of constellation history and is still in operation today. Recently, other countries and regions have been building their own positioning and navigation systems in addition to the GPS of the United States. For example, Russia's GLONASS has a satellite orbit and configuration that places emphasis on coverage of the polar regions. Another example is Japan's QZSS, Quasi-Zenith Satellite System. QZSS supplements GPS, and its orbit is designed so that the satellite is visible at a high elevation angle over Japan for a longer period of time, as shown in the figure on the right, so that positioning signals from the satellite are not easily intercepted in high latitude areas, mountains, and urban areas in Japan. Next, as a representative example of a satellite constellation for Earth observation, I will introduce the constellation by planet. The constellation, named PlanetScope, consists of about 200 3U CubeSats and can image the entire Earth daily from low Earth orbit with a GST ground sampling distance of about 4 meters. The SkySat series consists of about 100 kilogram satellites capable of higher resolution observations of 50 centimeters. Like PlanetScope, these satellites are placed in low Earth orbit. The SkySat series is capable of imaging areas of interest with high resolution. Another application is the satellite constellation by Spire. The constellation of Spire is based on a 3U-sized CubeSat and is operated with about 100 satellites. The orbits are arranged in various orbital planes from equatorial orbit, middle inclination orbit, and SSO to cover the entire Earth. The missions of the Spire constellation are as diverse as shown here. These missions are mainly realized by receiving radio waves for the purpose of weather monitoring, ship tracking, and so on. GNSSRO radio occultation is a method of estimating the temperature, pressure, and humidity of the atmosphere that causes the delay or refraction of signals sent by GNSS satellite as they pass through the Earth's atmosphere. A wide range of data can be obtained by observing the GNSS satellites in various positions between the GNSS satellites and the satellites in the constellation. GNSS-R reflectometry is a method to investigate the properties of the Earth's surface by analyzing signals reflected from GNSS satellites on the surface of the land or sea. GNSS-R can characterize sea ice classification and soil moisture. AIS and ADS-B are signals used to track the position of ships and aircraft, and these signals can be received by satellites for global tracking. Hawkeye 360 is a satellite or satellite constellation that detects and analyzes RF signals from satellites to locate and understand the activity behind them. The satellite receives a variety of radio signals from around the globe and analyzes them to locate their sources and analyze their activity patterns. For example, it may be possible to determine the status of smuggling and illegal fishing. SDR, software-defined radio, can receive a wide variety of signals such as AIS and ADS-B over a wide frequency bandwidth. The orbits are mainly low polar orbits, and global observation is possible. Up to here, I have introduced various applications of small satellite constellations. Chapter 3 describes the theory behind these examples, including orbit dynamics and orbit control, which are key to the design and utilization of constellations. One of the most important aspects of satellite constellation design is the design of orbits and placement of satellites within these orbits. The Walker constellation is a pattern that describes in a standardized manner what orbits to use and how many satellites to place in each orbital plane to ensure a uniform arrangement of satellites around the Earth. In the Walker constellation, each orbit consists of a group of circular orbits with the same inclination and altitude while maintaining a uniform spacing in the equatorial plane. In such a configuration, each satellite in the constellation is equally subject to the same perturbations, so their orbital altitudes, eccentricities, and inclination angles are commonly maintained at the same values. As a result, orbit control to maintain the constellation configuration is simplified. An example of Walker constellation is shown in the figure on the right. The Walker constellation is represented by the parameters shown here. First, the orbit inclination angle, I. Second, the total number of satellites in the constellation, T. And third, the number of orbital planes, P. In this case, the number of satellites in each orbit is T over P, and the phase difference between satellites in the same orbital plane is 360 degrees divided by the number of satellites. Each orbital plane is equally spaced with 360 over P degrees in terms of the ascending node in the equatorial plane. The fourth phase parameter F is the phase difference between satellites in orbit adjacent to each other, where the true anomaly difference is F times 360 over T degrees. One example of a constellation that uses the Walker constellation pattern is GPS. In many cases, other constellations can also be expressed using this Walker constellation pattern. In the previous slide, I mentioned orbital perturbation, which is an effect that causes the orbit of a satellite to deviate from the ideal two-body problem motion governed by the gravity between the two bodies, Earth and the satellite. In an Earth orbit, there are various sources of perturbation, such as the effect of the oblateness of the Earth, the gravity of the Moon and the Sun, atmospheric drag, solar radiation pressure, and so on. The Gaussian planetary equation expresses how the orbital elements of the satellites are changed by the forces of these perturbation forces. The equation shows the time rate of change of each orbital element when there are three acceleration components: T, perpendicular to the orbital plane, R, acceleration from the Earth to the satellite, and S in the direction of the satellite's velocity in the orbital plane, which forms a right-hand system with T and R. Using this equation, we can predict the long-term orbit change based on the perturbation force received. Please refer to another lecture for the details of orbital elements. As an example of perturbation, I will illustrate the effect of perturbation due to the oblateness of the Earth. The perturbation force due to the oblateness of the Earth is often called the J2 perturbation, because the coefficient J2 in the harmonic representation of the gravitational potential of the Earth corresponds to the effect of the oblateness of the Earth. The effect of J2 perturbation first produces an average time rate of change for the right ascension of the ascending node, omega, as shown in the upper equation. The semi-major axis, eccentricity, and inclination of the orbit determine the time rate of change of capital omega due to the J2 perturbation. Similarly, the time rate of change of omega is given by lower, small omega is given by the lower equation. Here, I will explain the sun-synchronous orbit, which is a satellite orbit utilizing the perturbation of large omega. In the right figure, the sun is in the center and the Earth orbits around the sun. If there is no perturbation, the orientation of the orbital plane does not change in the inertial coordinate system as shown in the red line. So the direction of the sun relative to the orbital plane changes with the seasons. In other words, with the changes in the position of the Earth in its orbit. If the satellite is injected into an orbit where the perturbation of the ascending node omega has an appropriate value, the orbital plane will gradually rotate in the inertial coordinate system as shown in blue due to the change in omega. And an orbit where an angle between the orbital plane and the sun does not change much with the seasons can be realized. This is called a sun-synchronous orbit. Sun-synchronous orbits are often used for Earth observation satellites because the altitude of the sun is almost the same throughout the year, and the same observation conditions can be maintained. Now, you may recall that the Volga constellation causes the satellites in the constellation to be perturbed nearly identically, so that their orbits are nearly aligned with each other. However, in order to keep the constellation configuration unchanged over time, the orbits of each satellite must be corrected from time to time. In addition, when operating a large number of satellites, it may be necessary to temporarily shift the orbits to avoid collisions with other satellites around the Earth. For these reasons, orbit correction operations that slightly change the orbits are necessary to maintain the constellation. For such small orbit corrections, the dynamics expression shown in the Hill equation below is used. Here, the position of a satellite flying in the vicinity of the reference satellite orbit, which is assumed to be a circular orbit, is expressed in the rotational coordinate frame shown in the right figure, and its time variation is shown. The Hill equation is a linear differential equation and can be solved analytically. The analytical solution is shown here. Given the initial conditions of the relative position and velocity from a reference satellite, the relative position and velocity after a given time can be calculated using this equation. Given a target orbit to be reached by orbit correction, the delta V to be generated at departure, and the delta V required at arrival at the target orbit can be calculated from the current relative position and velocity of the satellite and the time of flight to the target orbit. Then, by exploring the departure and arrival times, an orbit correction plan can be developed to achieve the target orbit with the smallest possible delta-v. Chapter 4 provides an overview of the various challenges in realizing a small satellite constellation. After explaining some technical issues first, I will also discuss the regulatory issues. First, let me introduce some of the tech challenges in satellite design and manufacturing. First and foremost, since a large number of satellites need to be manufactured, it is important to reduce costs. Standardization of design and establishment of a mass production process are key to this. Another issue is satellite reliability. Because the constellation consists of many satellites, the failure of a few satellites will not cause catastrophic damage to the entire constellation. However, satellite reliability is important to avoid increasing satellite manufacturing and launch costs. Communication capability is another important parameter in constellation performance. In the case of remote sensing, a high capacity of data communication is required to perform observations over a wide area with high frequency. And in the case of satellite communication services, high communication capacity is also required to support the communication of many users. In such cases, high-speed communication is required not only for communications to relay data between satellites in some cases. As an example of a technology that achieves high-speed, low-latency communications, optical communication instead of RF-based communications has recently been required. Next, I will present the challenges in launching, deploying, and operating satellites for constellations. The most important issue in launching satellites for constellation is to reduce the cost for launching a large number of satellites. To achieve this, it is effective to use commercial launchers and to launch a large number of satellites simultaneously in order to reduce the launch cost per satellite. For example, Starlink of SpaceX is designed to be flat, as shown in the right figure, and the number of satellites per launch is maximized by stacking satellites to make maximum use of the fairing volume. Another issue is the importance of accurate orbit injection for constellation satellite deployment. However, there is a limit to the accuracy of orbit insertion by the launch vehicle. Also, in constellation orbit design, satellites need to be evenly spaced within a single orbit plane, as in the case of the Walker constellation, and such orbit insertion is sometimes difficult to achieve by a launch vehicle alone. A solution to this problem is to use an OTV, orbital transfer vehicle services, such as that of D-orbit, to inject each satellite into the desired orbit. Alternatively, the satellites can be equipped with a propulsion system and have sufficient orbit correction capability to complete the transition to the desired orbit by themselves. Satellite operations require a large number of satellites in a constellation to be operated simultaneously, which demands a large amount of manpower and is highly prone to human error. To solve this problem, it is necessary to automate these tasks to save manpower and improve the reliability of satellite operations. The easiest tasks to automate include monitoring satellite status from telemetry, planning operations based on satellite status and observation requests, and executing commands. Some of the more advanced automatic functions include automation of orbit maneuvering to avoid collisions with other satellites or debris, and to adjust the satellite placement within the constellation. Another interesting and unexpected challenge arises from challenges in the cost the changes in the cost of satellite launches. Changes in launch cost have a definite impact on the determination of what satellite size and satellite specifications are most cost-effective. For example, if launch costs fall, the cost-performance balance shifts toward launching larger, more powerful satellites. Therefore, in the future, it may be possible to build constellations with larger satellites or with a larger number of satellites. Constellation operators will need to keep a close eye on these trends. In addition to the technical aspects, there are other issues that are related to legal regulations and policies. First, the most recognized issue is to prevent the growth of space debris. The problem of space debris has been discussed in various contexts, and it is becoming more and more important for constellations that need to launch many satellites. In order to control the proliferation of space debris and realize the constellation in a sustainable manner, it is necessary to ensure that each satellite is disposed of after its mission and to prevent collisions with other satellites and debris during operations. A propulsion system that makes this possible is considered to be almost indispensable. Another issue is in terms of radio frequency utilization. With the widespread use of satellite constellations, the use of radio frequencies to operate these satellites is rapidly increasing, and radio frequency interference is becoming a major problem. Radio frequency interference can degrade the quality of the satellite's communications and affect the use of other terrestrial radio frequencies, making it increasingly difficult to coordinate frequency assignments. It has recently been suggested that some constellations may emit radio waves at specific frequencies, affecting astronomical observations. It will be necessary for constellation operators and astronomers to work together to resolve this issue. One solution to these radio frequency issues is the use of optical communication technology. Optical communication technology has already begun to be used in constellations due to the increasing demand for faster communication. Light pollution, a phenomenon in which the night sky is affected by brightness of the light originating from satellites, has become a significant concern, especially for astronomers and stargazers. The number of satellites in low Earth orbit has dramatically increased, and satellites reflect sunlight, creating a noticeable rise in light pollution. As you can see in the right picture, the light pollution from satellites can obscure faint celestial objects, making it difficult for astronomers to conduct observations. This is especially concerning for the detection of near-Earth objects, NEOs, and other faint astrophysical signals. Companies are working on reducing the reflectivity of their satellites. For example, SpaceX has experimented with dark coatings and sunshades to minimize the brightness of their Starlink satellites. The effects of satellite re-entry on the atmosphere have also begun to draw attention in recent years. When satellites re-enter the atmosphere, they undergo extreme mechanical and thermal stresses, leading to the release of various gases and particles. These include metal oxide particles, chlorine, and nitrogen oxides, which can affect atmospheric chemistry. Also, substances like chlorine and nitrogen oxides released during re-entry can contribute to ozone layer depletion. This is a significant concern as it impacts the Earth's protective ozone shield. In Chapter 5, I will introduce the future direction of small satellite constellations. In addition to the possibility of realizing more advanced constellations, I will also discuss formation flights, which are missions using multiple spacecraft as well as constellations, and the possibility of constellations in regions beyond Earth orbit. The future of small satellite constellations may be transformed by technological developments. Examples of technological developments include further miniaturization, lower manufacturing cost, advances in communications technology, and the introduction of artificial intelligence technology, which could lead to the realization of constellations that are operated and maintained semi-automatically at lower cost. The various issues discussed in the previous section and are also expected to be solved through technological development. In such a future, for example, internet access in remote and developing countries will be further enhanced by a constellation of low Earth orbit satellites. In addition, disaster monitoring constellations will be put to practical use to provide information that can be directly linked to disaster response immediately by precisely grasping the disaster situation in a short time with a higher time resolution. There are many other possible directions, and I hope that the audience of this lecture will come up with many ideas and contribute to the realization of these ideas. Formation flight is a satellite utilization concept that is similar to constellations. A formation flight is similar to a constellation in that it is a mission using multiple spacecraft, but there are differences in the placement of the spacecraft and their objectives. While a constellation is a global arrangement of satellites, formation flight is a technology that achieves a single mission by maintaining and controlling the position and attitude of multiple satellites flying in close proximity to each other. As shown in the lower two figures on the right, formation flight has the potential to realize advanced astronomical and Earth observation missions that are not possible with a single satellite, such as a large aperture optical system by using multiple satellites to form a mirror, or high-precision imaging by interfering with observing data from multiple satellites. This is a possibility that cannot be achieved with a single satellite. While the position control of constellation satellites often does not require high precision and each satellite rarely works in cooperation, formation flights require the cooperative control of multiple satellites. The formation flight missions so far has demonstrated sub-meter accuracy, but various research and development efforts are underway to achieve millimeter or better control accuracy in the future. It is expected that this will enable scientific observation missions of a practical level by formation flight. Let's go back to constellations. Up to this point, we have basically discussed constellations built in Earth orbit, but constellations beyond Earth orbit have also been considered. Here are some examples. In interplanetary orbits, it is possible to achieve an orbit that leaves the Earth and returns to the Earth once a year by utilizing Earth swingby. This is called a circular orbit. By placing multiple spacecraft in such circular orbits at intervals, we can maintain the condition in which any one of the satellites returns to the Earth at a high frequency without leaving the Earth too far. Such a configuration makes it possible for one of the spacecraft to fly to explore objects that suddenly approach the Earth from outside the solar system, such as interstellar objects or long-period comets, by using the Earth swingby. In addition, even when there are no such objects to be explored, The satellites can fly by near-Earth asteroids and AEs approaching close to their respective circular orbits, so that a regular and frequent asteroid flyby exploration can be performed. Finally, let me summarize this lecture. In this lecture, 4 points were discussed. One is, with the advancement of small satellites, satellite constellations that cover the entire Earth by placing many satellites in complementary orbits have been planned and realized. The typical applications of constellations are navigation, communications, and Earth observation, but other applications are also emerging. For example, weather monitoring and ground activity monitoring using radio frequency observations. The background theory behind the orbit arrangement design and orbit maintenance methods, which are important in constellation design and operation, was introduced. In addition to technical issues, legal and regulatory issues have been identified for the realization and evolution of small satellite constellations. By solving these issues, more advanced and practical constellations are expected to be realized in the future. With this, I conclude this lecture. Thank you very much.